So let's just sort of review a little bit about light and color, okay, and its energy. When we talk about the color of light, what we're doing is specifically talking about its energy. So again, we have red on one end, then Roy G. Biv and violet at the other end. And going from this direction to this direction is increasing energy, right? And then decreasing wavelength or increasing frequency. So those are the things that are going on. So scientists did this experiment. They took gases like neon, for example, or helium or argon. Noble gases were used for this a lot, but they could have done. You can do any gas for this, like nitrogen, oxygen, things like that. And you take and you make a lamp, so like a light bulb essentially, that contains these elemental gases inside the light bulb. The slight difference is rather than having a filament, they use an electric field, almost like you imagine you see in the Frankenstein movies where there's electric like lines going around, and you know that's the kind of light bulb they were generating. It didn't have sparks in it. It didn't have very much air or anything in it, so there wasn't much to carry the electricity on. But they would generate these called discharge lamps, and they would fill them with different kinds of gases, and they would shine that light. Okay, so this is the light, and this is like the element in a bulb, and they would shine that light at a prism. And if you take a prism and you hold it up to the sun and you look at the colors that come from the prism, but basically you see all the colors of the spectrum. You see Roy G. Biv entirely, right? And that's what we call white light. And what they did with these bulbs is they ran the light through a prism, and what would happen is it would separate into, for example, into red, right, and then Roy G. Biv kind of things. But here's the thing, and so on one end would be red, on the other end it would be violet. I don't have violet selected right now, so we'll go like that. And then they would image this on like a piece of film, or they would see it. Actually, you could actually see it with their own eye. And what they saw was not a continuous spectrum, but they saw just regions of brightness like this. And so a lot of the other wavelengths were missing, and only very discrete wavelengths were showing. Very small ranges of wavelengths were showing. And so what did that tell them? What it told them is that the light coming out of a bulb, for some reason, right, was only represented by a small handful of wavelengths. So this is what became known as the line spectrum dilemma, because classical physics sort of predicted that it would be all kinds of light that you would see. Okay, so this is what actually led to the idea of quantum mechanics, this sort of idea. And the idea was this, is light energy is not continuous, but it's discrete, okay? So discrete means individual wavelengths that we're seeing. Now, not everything does this. In one of the labs earlier, I showed you an image that looked like this. And in fact, what this color spectrum is generated from is they take a piece of iron, or a particular type of steel, actually, in this case, and you heat it, and as it gets hot, it begins to glow different colors, and you can relate the colors to the temperature. And it turns out, as you heat this object, you can get essentially all colors of the spectrum out of it. And so the question was, like, why did some things give us continuous spectra while something didn't? And so this is what led, again, to the idea of quantization of light. That is, quantization means it's broken up into discrete values, where some things didn't. So it was up to a Danish physicist named Niels Bohr, and Bohr came up with a model, okay, to help explain why some elements gave line spectra. And his model actually worked almost perfectly, as at least for the state of the art as it was then, for helium or for hydrogen atoms, but it didn't work for things beyond hydrogen. So we'll talk about that maybe a little bit as we get towards the end. But for now, let's just sort of try to understand what the general explanation for line spectra is. And so it works with the planetary model. So I'm going to give you a little bit of background, right? And again, it's kind of seems like it's unrelated, but it's actually physics. If I have, this is the ground, right? And usually I stand on something and jump off of it, but since I don't really want to do that on a video. It'd be awesome to get a picture of me like injuring myself for the sake of science, but I don't think it's probably not really worth it that much. So, and there's a shelf up here, right? And I'm standing on top of this shelf. Now, the shelf wouldn't be this tall. I just don't have room to draw it quite right, not to scale, right? And I jumped off like this, right? Where do I have more potential energy? Where do I have more energy in this system, right? And the answer is when I'm up at the top and on the bottom, which, you know, for me would be like this. But anyways, at the ground level, right, I'm at my lowest energy. And I know that because to get up to the top, just like physically, I have to climb up there, right? So I have to expend energy to go up there. So that must be the higher energy state, okay? So this is an excited state or a higher energy state. And this is actually called, this lowest energy is actually called the ground state. And the difference in energy here, right, is actually just the potential energy. And the reason there's a difference in energy there is because gravity. Gravity is attracting me towards the Earth. I'm high up, and I'm not going to get into all the equations for it. They're fairly simple, but the further up you go, the more energy you store. You know this because you have to climb up. Right, and then you release all that energy. When you jump, you convert it into kinetic energy. You hit the bottom, right? Some of that gets converted into heat, and then you lose all that potential energy. So, having said that, Bohr's planetary model is set up like this. If you have a central part to the atom, the nucleus, right, and it has positive charge, the electrons can exist in regions around the nucleus that looked like this. So I just went off and I got a circle drawing tool and made that. So this is the planetary model. The nucleus in the middle has a positive charge, and the electrons exist in what are equivalent to the orbits of the planet. So later we'll learn that these in modern chemistry are called orbitals, but they got their name from the idea of orbits, even though it turns out things are not actually orbiting like we think they did back then. But here's the deal. So the ground state is this one here. This is n equals 1. This would be n equals 2 and n equals 3. So he called the n's, he called them principal quantum numbers, and we don't really need to know too much about it other than maybe its name. Okay, and the ground state is n equals 1, and n equals 2 and n equals 3 would be the excited states. Now, he described this for hydrogen. So if you recall, hydrogen has 1 proton in the nucleus and has 1 electron. So we're looking at 1 electron out here somewhere. This would be at its lowest energy state. Because remember, like when you have the planets, everything's sort of attracted to the sun, right? And so this is the lowest energy, and then all these higher energies would be excited state. So in hydrogen, in its ground state, it would be in this lowest energy level. On the other hand, if it was at an excited state, so let's say we put it here, right? Then it could relax. That's what the equivalent of jumping off is for me, jumping off the shelf, right? The equivalent is called relaxation. It's not when you jump, but it is when this happens. And it could jump down to this lowest energy level. And what Bohr said was there is the electron can only exist at the energy of the different principal quantum numbers, and it can't exist between. So it had to jump from high to low, okay? And then when it did this, it had to release energy. And this energy, right, would be the light emitted, okay, by the atom. And if you think about it, because this energy level is always the same, you would only get one wavelength of light out. Now, if the electron started further up, let's say it started at n equals 3, right, and jumped down to here, then you would get more energy, because if it doesn't stop in between, it has to go from 3 to 2 or 3 to 1. So if it went from 3 to 1, then what you would get is you'd get a different wavelength of light out. And I try to make those waves shorter than these waves because it had started from a higher energy but ended up at the same ground state level in the hydrogen atom. You would get a higher frequency of light. And then this could go on to explain, right, Roy G. Bibb, why we saw in our line spectrum dilemma, why we only saw certain wavelengths of light occurring. And it was because of these quantum leaps, right? These jumping from discrete energy level to discrete energy level. Again, this whole idea of quantum means it's broken up into discrete values, and Bohr's model did a very good job explaining that, and that's the little explanation that goes down here. So basically, Bohr's model helped explain line spectra by proposing discrete or quantized energy levels. I can't write tonight. Energy levels in the atom. And in particular, he was only successful, at least initially, explaining hydrogen. But then he was able to do a helium ion. He was able to remove. So it really only worked for systems with one electron in it. And then after that, it didn't work. And it was much more complicated than you might think to sort of come up with a solution for like 2, 3, and 4 electrons. Okay. And the real solution still actually kind of eludes people. They have computer models of them, but mathematically it's unsolvable at a certain point. So by he proposed quantized energy levels in an atom, and the electrons could only jump between levels, producing discrete energy levels, or producing discrete energies of photons. Okay, now I want to say one other thing though, because I've only talked about light being emitted. It turns out they only absorb certain wavelengths of light too, so when you pass light through them, then electrons have to jump from a low energy level to a high energy level like this, and what they do is they absorb that same wavelength of light that they would emit, okay? And if you think about, like, this sounds kind of weird, but how do we know what elements exists in galaxies like so far away from us? And the way we do it is actually we can look at the line spectra for the elements, the light that comes from those systems, and we can also look for missing wavelengths of light, which tells us what elements are also existing in that system. And so we have some fairly good ideas about what elements exist outside of our own universe, our own galaxy, I should say. Outside our universe, I don't know if we can do that. But anyways, yeah, outside our own galaxy. Yeah, so modern atomic theory and quantum mechanics is just based on this quantized or fixed levels of energies for the orbits.